Assalamualaikum sir, myself Durjoy Kumar Shaha. Today I will explain a simple car parking system using a block diagram and flowchart. We are considering a parking lot with a maximum capacity of 9 cars, that is 2 plus 5 plus 2 plus 9. That's we got using our ID. Here is the block diagram. The block diagram. The process begins with a keypad where the user inputs data. This data goes to an encoder, then to a register, and finally to a converter to check if the parking is full or space available. We also use a clock and a counter to keep track of time and the number of cars. Entry and exit sensors detect whether a car has entered or exited. Based on that, the counter updates the car count in the register. Two timers are used. Timer 1 activates full display when the lot is full. Timer 2 activates the space available when parking is available. Next, in the flow diagram. In the flow diagram, the system starts with the keypad and the user sensors to detect car movement. If a car enters, the system checks if true, it increments the car count. If false, it decrements the count, indicating an exit. Then it compares the car count with the maximum value, which is 9. If the count equals 9, it displays full, otherwise it displays space available. The system helps efficiently manage a small parking system lot by using sensors, timers, and logic to show real-time status. This part of the explanation focuses on the technical functioning of our parking system using both the block diagram and circuit diagram. The block diagram shows how all the components are connected, like the keypad, sensor, counter, timer, and display unit. It gives us an overview of how the system is structured. The flow diagram, on the other hand, explains the logic behind the process, how the system responds when it enters and or exits, how it decided when to show full or space available. At the heart of the system, this is a 4-bit up-down synchronous counter. The counter, which is shown in the circuit below. The counter is triggered by the entry and exit sensor. When a car enters and space is available, the count increments. If a car exits, the count decrements. Once the count reaches the maximum value of 9, the system displays full and no more cars will be allowed to enter. This ensures the parking system runs smoothly, avoids overfilling, and gives real-time feedback through the display system. Now, in the second question, in this system, the monostable timer is used to control the display of the word full, which appears only once when triggered. On the other hand, the stable controller blinking of the message space available, which continues to blink as long as the condition is met. This blinking behavior is possible because the stable timer produces a continuous output, which is a perfect for signaling available space in a dynamic way. We also calculated the duty of cycle the signal using the given values. We found the data cycle to be 64 and the frequency would be 6 Hz. This means the signal blinks 6 times per second. The, this kind of timer logic is commonly used in electronic display system to alert users in real time, such as in the parking system or digital. In this configuration, we have set the timer to operate in stable mode, meaning it continuously switches between high and low states, creating a square wave output. This is what makes the message blink repeatedly. We calculated the time period T as 0.167 seconds or 167 milliseconds. The high time TH and the low time TL were determined based on a 64% duty cycle. So the high time comes out to be 106.88 meter per second and the low time is 60.12 millisecond. Using these values, we have calculated the required resistor R2, which is lower resistor, is equal to 1736.06 ohm, and the upper resistor R1 is equal to 1348.49 ohms. We also use a capacitor of 50 microfarad in the timing circuit. The diagram at the bottom of the page shows the stable mode where the timer IC is connected to a resistor and a capacitor to produce the necessary pulses. These pulses are sent to a display circuit that shows space available in a blinking fashion, making it easy to grab in attention. This kind of setup is commonly used in parking systems, counters, or any application where visual signaling is important. In the figure mentioned, we have two values. A represent value of the resistor connected in a B represents the value of the resistor connected to the center of the continuity. Since the full display is meant to be constant and not blinking, we have decided to use another timer in stable mode to manage the display other messages like space available. To ensure the smooth and reliable operation, we have designed this system by adjusting the duty cycle. This way, the output signal can be tailored as needed. In this part, in the design, we have considering that high time TH is 167 meters per second and the low time TIS TLS 0. Because of this status, the lower resistor R2 becomes 0 and the upper resistor R1 is calculated using the formula, which is 167 into 10 inverse 3 divided by 0.693. By substituting the value, we have got 4819.624 ohm. This value ensures the timer output ready signal suitable for the full indicator without any blinking, ideal for constant use. So in summary, we have used a combination of monostable and stable timers to control how messages are using the appropriate register value to shape the timing behavior. In this part of the assignment, we are focusing on the timing and state behavior of the way. Begin by noticing that the clock period is 1 millisecond and the timer operates with a high time of 106.88 milliseconds and a low time of TL of 60.12 milliseconds. That means the timer remains high longer it stays low, which is essential for how the circuit responds and transition between state. Now we look at the state table provided. It shows how the system behaves based on the current state and the input considerables. There are two main states, S0 and S1. The system transition between these states depending on the counter value. For instance, while in state S0 and for counter values 0 to 2, it remains in S0 and produces an output of 1, 0. However, at counter value 3, the state changes to S1. In S1, the counter values of 0 to 2, it stays in S1, but when the count reaches 3, again it transitions back to 0 and the output becomes 0, 1. The cyclical behavior helps the circuit manage and reflect changing input condition and possibility to toggle in the full display or other indicators depending on logic condition. In summary, this table guides us through the system sequential logic, ensuring we understood how states change over time with the input and how output is controlled accordingly. Let me know. Next, we design a two-stage systems S0, S0 and S1 to control the blinking logic of two outputs A and B. The transitions are gathered by a counter. In stage 0, the output is 0 and A is equal to 1 and B is equal to 0. The system stays as long as the counter is less than 3. Once the counter reaches 3, when transitions to S1. In state S1, the output switches A becomes 0 and B becomes 1. The system stays in S1 while the counter is below 3 and moves back to S0 when the counter hits again 3. This forms a loop where the output toggles every 3 clock cycles. Now looking at the Verilog code implementation, the module is named efficient blink. It takes a clock and a reset as inputs and produces two outputs, A and B. We declare a 3-bit counter and single bit state register. On reset, the FSM initializes, the state is set and to 0 and the counter is clear, and the outputs are fed to A1, A is equal to 1, B is equal to 0. On every positive edges of the clock, the counter when it reaches through 3. It resets and the FSM toggles through the other state. Based on the current state, the output A and B are updated accordingly. This FSM demonstrates a blinking pattern controlled purely by digital logic. By digital logic, it highlights how we can use state machines and hardware description languages like Verilog to implement timing-based logic that would otherwise require manual toggle or external control. Now, in the fourth question, now we're gonna talk about the limitations. There are plenty of limitations for the developed system. There is a point of issue that arises, which is that the counter is not modified to only count 9. Since it is a 4-bit counter, it will go to up to 15. So if a count comes in despite the display showcasing full, the sensor will increment the counter for a greater capacity. The counter needs to be of a higher bit, and that number that is given to the decoder has to be increased accordingly. Has to be increased accordingly. The registers need to be adjusted as well as the specification, which is bit to use, depends on the incremented capacity. Thank you, sir. That's all for today.